started the recording. We're happy to have Daniel tell us about the Madsen-Weiss theorem and have him pronounce it with a better German accent than me.
Yeah, that's some pressure now. Now I can't do it. All right, give me one second here. So seems like I cannot see the comments while I'm sharing my screen. So I'm trying to access the meeting through my computer as well, just in case that anyone can write something on the chat or something, and so that I can see it.
I could also like interrupt if you ignore a comment in chat and just tell you.
Okay, yeah, that works. That works then. All right. So today I'm gonna tell you a little bit about the Madsen-Weiss theorem, and we have a very straightforward objective for the session. It's pretty much getting to understand the statement. So we're gonna start from a very fuzzy, hand-wavy statement of the Madsen-Weiss theorem, and hopefully we're going to have at the end, by the end, a better idea of what that statement looks like, and really what are the ingredients involved, right? So that's the first statement, the first objective, the statement, and then the second objective is kind of to show why one would expect such a result, and that's basically what's used for the proof. So the main idea of the proof, which is going to turn out to be a sort of scanning map similar to what we did during the semester in a couple of times. All right, so what is this Madsen-Weiss theorem? So let's start with this hand-wavy statement. That's our first step here. All right. So this is what the theorem says. It says that the homology of mapping class groups of surfaces in a stable dimension range is isomorphic to the homology of a certain infinite loop space. So again, this is very wavy, and basically what it's telling us is that we have this. Yeah, this one. Right. So what's here in quotes is the following: is we have this homology of this thing, the mapping class group on the left. I'm assuming that, like me, some of you don't know what this is. Some of you might, but still, I'm going to say what that is more precisely. Homology of this group related to a surface, right? This is mapping class group of a surface S. Right? And on the right-hand side, we have this homology of some infinite loop space. Right? Actually, I'm actually not telling you right now what that infinite loop space is, and that's something that we're gonna try to make more precise. So this is what I mean by taking a hand-wavy statement and try to make it more precise, understanding this, and kind of fill in the gaps so that we know what every ingredient involved is, and we can kind of appreciate what the result is actually saying. All right. A small comment here is that on the left-hand side, I am talking about the homology of a group, and it's going to turn out to be a discrete group. So really, I need to tell you what that is. So we're going to take it pretty much as a definition that the homology of a group is going to be the homology of a KG1. Right? So the homology of an island space, KG1. All right, so let's take this hand wavy statement and make it more precise. All right, so there are two questions that right away are very natural. First question, what is the mapping class group? Already hinted at this. At least I didn't know what it was. And the second question is, what is this mysterious infinite loop space? So we're going to address that. So first answer is basically it's just going to be definition. So let's see what that is. So what is the mapping class group? Right. So let's assume that we have S a connected closed orientable surface, right? And one can think of the orientation preserving homeomorphisms of F onto itself, right? That's a bunch of maps. So we have that bunch of maps that are orientation preserving homeomorphisms. We're going to denote that by homeo plus. The plus stands for the fact that it's orientation preserving. If we drop the plus, then we're dropping the orientation preserving condition. Then we're going to work with this. All right. So what happens when I consider this bunch of maps, this set homeo plus of S? All right. So does this have a group structure? Well, yes, of course. We have maps from S onto itself, and their homeomorphisms. So we have composition. So that's nice, right? So it has a group structure. Does it have a topology? Then again, we're dealing with maps, so the natural choice is the compact element topology. So again, yes. So we're dealing with a topological group, homeo S. All right. What can we do with this topological group homeo plus S? Right. So one thing we can do is we can mod out by homotopy. Right. So homotopy defines an equivalence relation on this set, and we can mod out by this relation. Right. Equivalently, we can mod out by the component of the identity and of the identity of this. This homeo plus with this not here or this zero there means the component of the identity. That's like the way we denote that. But really, these are equivalent things. Modding out by homotopy or modding out by the component of the identity, those are equivalent things, right? And we get some, right? We get this quotient group, and this is exactly what we're going to call a mapping class group. So the mapping class group of a surface S, which will denote MCG of S, is precisely what I told. Right? We take the maps and we mod out by homotopy, or equivalently, we take the maps and we mod out by this component of the identity. Or another way to write it is to write it as pi zero of homeo plus, right? Which is the same. Like we know that at least these two are clearly the same thing. Okay, so all of these notations kind of work for the mapping class group. I believe that throughout the hour, the talk, we're going to just stick to MCGS. But the point is that we know what it is. It's a bunch of maps. They are homeomorphisms, orientation preserving homeomorphisms, and we are modding out by homotopy, and that's where we get our mapping class group, right? So if we have more structure, say if S is smooth, then we can replace homeomorphisms by diffeomorphisms, right? This is very natural. We have this extra structure, why not use it? And then we can, we define, if S is smooth, we define the mapping class group of S just with the same construction by using diffeomorphisms, okay? Actually, yeah. So homeo is, let's say, like a little bit more general, but we are actually going to be talking about this case. So really, we're gonna be thinking of this. Right. Okay, so let's see an example of this. Right. So what is the mapping class group of S2? Okay. So let's think of it in terms of homeomorphisms. It's going to turn out to be the same if we think of it in terms of diffeomorphisms. But let's just say homeomorphisms. Any homeo of S into itself right. Okay, so this is wrong. Any orientation preserving. Right, sorry about that. So any orientation preserving homeomorphism of S2 into itself, it's homotopy equivalent to the identity map. Right. So it's basically the class of rotations of S2. And that's clearly we can find a homotopy to the identity map. So we basically get that the mapping class group is the class of the identity. Okay, so a trivial group. Okay, and there's this other notion. This is really not important right now, but we made a choice here of only considering the orientation preserving mass, but we could have considered every homomorphism, and then that's where we get the extended mapping class group, and of course we get something different because we get more maps, and in this case, well, we get actual either the homomorphism that's identity or the one that switches the orientation of S, right? So we get two things. We're basically getting a Z mod 2Z for this extended mapping class. But I mean, this is just a comment. We really don't need that for today. All right. So now that we have an idea of what the mapping class group is, we can kind of head towards answering the second question. Remember, the second question was, what in the world is this infinite loop space that we have on the right-hand side of the theorem? Okay, so first, I guess this is a little bit in the middle of everything, but part of a motivation of the for the theorem in general was this conjecture by Mumford. They didn't know too. His conjecture is about the rational stable cohomology of the mapping class group surface, and he conjectured that I'm sorry, this is that right, that this rational stable cohomology is a polynomial algebra, right? So basically, right, so this is the type of result that we want for this mapping class group, that the cohomology has a structure of this polynomial algebra, right? Well, where the t's don't really mean variables, like independent variables. I mean, they may have relations. The point is that it's an algebra over the rationals. Okay, so this was kind of like an idea motivating that. So what Mumford did was he proposed like a guess for the cohomology, and then I guess that the Madsen Weiss theorem is a sort of an answer for that actually gets this as a corollary. All right, so let's keep going. This was a little bit of like where the problem, like what motivates the problem. All right, so now, like I said, toward this definition of this infinite loop space. Okay, so this will take a little bit more work than the answer to the first question. The answer to the first question was just a definition, the definition of a mapping class group. But in order to get this infinite loop space, we're gonna have to think of the problem a little bit and see how it slowly appears. Okay, So we're going to start to think about the homology of this mapping class group. And we know that this is the homology of a K mapping class group 1 by definition. I told you before that this is a discrete group, so I need to give you kind of a way of a definition of the homology. And it's going to be the homology of this guy. And so we're trying to find this. Okay, so if we want to find really the homology of an Heisenberg-MacLane space, well, we better pick one. So what we're going to do is choose something that's going to turn out to be a K MCG1. All right, so what is this space? All right, so let's see as R infinity be the space of all smooth oriented subsurfaces of R infinity which are diffeomorphic to S. And here the C stands for configuration. So let's think about this for a second. The space of all smooth oriented surfaces of R infinity diffeomorphic to S. So what that means is, I have S embedded in however many ways I want into R infinity, right? So there are many ways of having kind of like, quote unquote, a copy of S inside R infinity, and this is what we are considering. All of this copies of S inside R infinity. By copies, I mean things that are diffeomorphic to S. Okay. Okay. So the claim is that this space is the Eilenberg-MacLane space that we want. Okay. So let's see why that is true. Okay. So we can think of C configurations of S in R infinity as this union of the configurations of N in Rn, as N grows larger, right? As kind of like embeds in Rn in however many ways it can, and then N gets larger, and considering all such embeddings really retrieves this possible embeddings into R infinity. Okay. And this union, and here we have inclusion maps. So really, we're thinking of C as R infinity as a direct limit. So the topology that it has, I said before it's a space. I haven't really going to use topology. The topology that it has is the direct limit topology. Okay. So how else can we think about how can we think about C the configurations of S in Rn now? Like stop at one step, Rn, and how can we describe this? Okay, so one way to think of it is the orbit space of the space of smooth embeddings S into Rn, denoted by this embeddings of S into Rn under the action of the group of diffeomorphisms of orientation preserving diffeomorphisms. And why is this true? Well, like I said, configurations of S in Rn. Well, basically, what that is the ways that I can embed in a smooth way. I can embed S into Rn, right? But I have to mod out under this diffeomorphism group. And I'm not sure if I'm being clear here. So if this does not make sense, so let me know and I'll try to say it in another way. And so we embed S into Rn, consider its class under this diffeomorphism group, orientation preserving diffeomorphisms. And that's going to be your set of configurations Sn, Srn. Okay, so this is
you can kind of think of this E thing as like ordered configurations. It's like surfaces in Rn with a parameterization. And then the CSRN is like surfaces in Rn without a parameterization. if that's helpful for.
Yeah, exactly. So modding out under this action is kind of losing that, forgetting about that parameterization. Okay. Okay, so we have this maps from this embeddings into configurations. It turns out to be a fiber bundle, right? Just by the way that I described this here, it's kind of clear that I'm doing this map and then I'm modding out by diff. So really, what I have is this quotient map that has fiber, exactly what I mod out. Okay. Okay. So hopefully this makes sense. Up here, I am cheating a little bit because. Okay. So why am I cheating here, or best like skipping things? Because up here we're dealing of the we're working in Rn, so we're fixing like some step, and here we are saying that we have a map, and we're working now in R infinity, and I guess the description of what happens in Rn allows us to pass to R infinity by taking limits, and because limits are well behaved with everything that's happening here. Now, of course, I'm not being precise with any of this, but I just want to give a broad idea of what's going on. Like in general, that's going to be kind of the flavor of the talk. Given the idea of what's going on, I'm not going to talk on the details. But if I'm being completely honest here, of course, I'm skipping some things that happen here in between that allow me to define this map on embeddings of S into R infinity to configurations of S into R infinity. Right? All right. So after that disclaimer, we have this fiber bundle, and this has fiber diff, and the total space embeddings of S into R infinity is a contractible space. Again, this is another thing that I'm kind of just stating without actually giving you a good answer to that. Like, what is it? So this is the idea. To get this fiber bundle, we know what the fiber is, and we get this contractible total space, so that we can use the long exact sequence of homotopy on the bundle, and because of the contractible part, we get this isomorphisms. Okay, so this was the fiber. And this is an isomorphism given by the long exact sequence. Again, if any of the steps really seems crazy, we should stop and talk about it. But this is what's going on. All right. So I remember what am I proving right now? I'm proving that this thing is an Eilenberg-MacLane space for MCGS. But remember that MCGS, I said before, that is I0 of diff plus of S, right? So being an Eilenberg-MacLane space of MCGS means that pi 1 of this thing, of the configurations, should be isomorphic to pi 0 of this thing. Right? So hopefully this is clear. That's what we want to show that this is an Eilenberg-MacLane space. So really, what we want to show is that this pi here, when I is greater than 0, I want this right-hand side to be 0. Okay. So again, that's the thing. We need to prove that that is an island mechanics space. Okay, now I'm just gonna quote a theorem that's gonna help me exactly, do exactly that. So the Earl-Eels theorem says the following: that if S is a compact connected, possibly with boundary, surface, then the components of diff S are contractible except when S is S2, P2, or the torus, or the clamp ball. Right. So basically, if we stay away from this, from the surfaces, then the components are contractible. So we get the pi i's for the pi i's of S. I'm sorry, of diff S are 0 for I greater than 0. Yes, for I greater than 0. And hopefully everyone can see this. That this is exactly what the Earl-Eels theorem is saying. Okay, so let's use it in our case, and what we get is that, well, say if we have genus greater than 2, then we are staying away from these. So say that our original surface has genus greater than 2, then we have exactly what we want. Right? So if S is genus greater or equal than 2, then we have shown that configurations of S in our infinity is an Eilenberg-MacLane space for the mapping class group of S. Okay, so we showed this. So first step was to get this Eilenberg-MacLane space. But so far, so I claimed that I was looking for this infinite loop space, but so far there is still no sign of the infinite loop space. We gotta keep going. Okay, so now the next idea is scanning map. All right, what can we learn about S just by looking local? So this is kind of the idea motivating a scanning map is this. What information can I retrieve about S by looking local? How do we look local? So let's assume that we have an S, and my S is this surface. I just chose pretty much any surface. Since I said before that we wanted something with genus greater or equal than 2, then I'm just taking this with genus greater or equal than 2 to be to make it easier for me. Okay, so the idea is to take a ball, an n-dimensional ball, and just start scanning, start going to different points of the surface, right? So in reality, what we want to do is we want to have the surface really large, and we want to have the scanning quite small, so that if I move throughout R3, well, most of the times I'm getting nothing. So on the ball, I am getting absolutely nothing. But as I go near the surface, something starts to appear. And if the ball is small enough, then what I see, if I just have the information on the ball, what I see, it looks almost flat, right? Pretty much because S is smooth. So what I see is almost flat. It's kind of like a plane there. So I move it throughout, and that's what I see. Okay, so when I scan, when I use this lens when I use this lens to see what's going on in my surface, I can get either nothing or things that are pretty much planes. Okay, so with that in mind, so let's say that we have something that is pretty much a plane. It's almost flat, so we could get something like this when we zoom in. But really, if we are thinking about homotopy, then the homotopy, the space of almost flat planes in an M-ball has the same homotopy type as the space of flat planes. And this is kind of hand wavy, but the idea is clear, I hope. Right, so we might as well just work, since we care about homotopy, let's work with this. Let's work with this. The way we can get the right thing from the left one is we can kind of consider this this almost flat surface and find like its center of mass, and that gives me a plane that's tangent to that center of mass, and that uniquely defines a plane corresponding to this almost flat thing that pretty much is giving me something of the right-hand side type. Okay, so our scanning map really is getting things like this. Okay. Oh, okay. Of course. Since S was oriented, then that induces orientations on the things that we get. Just it's what is defined by S. Okay. So we're thinking of planes on an N ball, but we can replace that N ball, or pretty much think of that N ball as Rn, right? And consider the configurations of, or just consider planes in an in Rn, right? Planes in Rn, and that is the Grassmannian. Well, that is a Grassmannian. So what we get is we're really looking at the affine Grassmannian AG and D. Really, in our case, we have N2. We have planes, right? And here Jeremy told me to be careful with the term affine Grassmannian, because I could get into trouble if I use it wrong. So the point is that affine Grassmannian might have other meanings in other areas of mathematics, but right now what we mean by affine Grassmannian is planes in Rn that need not pass through the origin. So that's why the affine, the affine, what it means here is that it might not, the planes need not pass through the origin. Okay, so what's happening here? As we scan our surface S and we move around our bubble, our lens, we are getting points of the affine Grassmannian. And that's kind of lying, because I said that most of the times we get nothing while we scan, right? Most of the times we get an empty, a copy of Rn. So the way we fix this is, okay, so let's consider AG N2, sorry, N2 plus, where plus denotes the 1-point compactification. And the trick here is that, well, what we're doing is, well, we need an extra point of the affine Grassmannian to stand for the empty ball, right? The empty lens. So let's add a point to the affine Grassmannian, but by compactifying it, and we're going to say that that point corresponds exactly to the empty configuration, the empty two plane in Rn. Okay. All right, so now letting the lens move around Rn, what we get is a map from Rn union infinity that we think of as an Sn to this affine Grassmannian with that extra point that stands for the M2 configuration, or AG plus. So a valid question here is, wait, you said that we were scanning through Rn, and our lens is moving through Rn. What's up with this extra point? So we're just defining the map on this point at infinity to map to the compactification point here, the one that stands for the empty configuration. And that also kind of makes sense in the from a geometric standpoint, because if we are scanning a neighborhood of infinity, right? So if we're scanning something in Rn that's really, really far away, then we're definitely not getting any piece of the surface, right? Because we're too far. So it would make sense for us to map the point at infinity at the to this compactification point that stands for the empty configuration. So it kind of holds with the geometric interpretation of this map. All right, but what is this thing? This is a map from Sn to a space. But that is exactly how we define loops n of the space, right? The points of loops n are maps from Sn to the space. So really what we produce every time that we fix a surface and we scan, we are producing a point of the configuration of the loop space, loops n of the affine Grassmannian N2. Right. So finally the loops come into the picture. So here are where the loops appear. They really, we get them from the idea of scanning. So this goes back to one of the objectives of the talk, which is, why would you expect some relationship, some result that relates this mapping class group or this homology of the mapping class group and the homology of some loop space? And here we see, what lies behind this is the scanning map. The scanning map is what really makes these loops show up. All right, so we got our loops. Again, this is just some loops. We are looking for an infinite loop space. So we really want to see what that looks like. So we gotta keep pushing. Okay, so now we get to a sentence that might be not so clear. All right, so let's choosing the magnification to vary continuously with S, we obtain a map from configurations of S and Rn to this loop space. So what is this? All right, so what we did above was we chose one copy of S in Rn, and from this copy of S in Rn, we produced a scanning map that scanned all of Rn plus that point at infinity, and we retrieve the point in the loop space. Now we want to map from all possible copies of S in Rn. And for each copy, we want to produce such a map. Now there's this sentence, choosing the magnification to vary continuously with S. So why do we need that? What's the point in that. The point is that if we define a scanning map, that scanning map might not work for every possible way, every possible embedding of S into Rn, right? If we have a scanning map that scans with lenses of this size, just like in the picture, but the embedding of S is like this, well, then this lens is not going to do what I want it to do. It's not going to retrieve, almost flat things, right? It's too large. It just won't work. So depending on how we embed S into R3 in this case, or into Rn, we need to choose this lens appropriately, right? So that when we scan, we really do get that nice map from into the affine Grassmannian and eventually the point in the loop space. So defining this map in general is actually kind of tricky, right? It is just kind of tricky. If you think about it, the more you think about it, the more the trickier it gets. To just give like a plain right out a definition, it's not so clear. And actually, on the paper that I'm basing this talk on, what they say in words is, they say it is sensible. No, it is plausible to assume that one can choose a magnification to vary continually with S, right? So they're actually just saying like, it sounds reasonable, and it does. It does sound reasonable, but if you want to write it down, you might run into trouble. So the actual proof does not use this map. It uses this idea, but it goes through another step, right? It goes through another thing. Okay, so I just wanted to comment on this map that we get now from these configurations of S and Rn into loops N, right? And the fact that I am really not telling you how that is defined precisely. I'm just telling you that it makes sense for there to be such a map. All right. Okay. So I said that I wanted to produce an infinite loop space. So let's do that. We have to shift up N. We have to move to higher ends. Right. So letting N increase, we get a natural inclusion, and this inclusion is pretty straightforward. If we have an embedding of S into Rn, well, by A embedding of Rn into Rn plus 1, we can get an embedding of S into Rn plus 1. Right? So this arrow really makes sense. And okay, and we can produce a map that goes from loops N to loops N plus 1. Right? I'm not, again, this one is very clear. For this one, I'm not giving you the details right now. One way to construct it is to produce a map from, sorry, I'm dropping all the extra stuff, N plus 1. I'm sorry, there's 2 loops. So one way to produce this is to get a map like this and then apply loops N, and that induces a map exactly like we want. So that's one way to define such a map. And this maps that shift up allow us to take limits and define a map as we're taking limits, on the limit. Getting a map from configurations of S in R infinity, which And as you recall, it was the first thing that we defined. So it was really the object. This is the object that is a K mapping class group of S1 into the loop space. Right. So now the result. I mean, it looks like there's a little bit of hope for the result that we wanna prove or state actually. All right. So I'm gonna keep going, but just give you a second if there's any question on this step. Or if Jeremy wants to comment or something.
Oh yeah, maybe one thing to say is that this loops infinity AG infinity 2 thing, you shouldn't you should parse that like the whole thing is a space, but it's not like loops infinity of some space called AG infinity 2. So these AGNs get more and more connected as n goes to infinity. So like if you wanted to just look at the spaces, you'd think maybe AG infinity 2 should be contractible, but like loops n shifts the homotopy groups down. So like homotopy groups of AGN are 0 in a range increasing with n, but then loops n of it shifts it down by n. So you end up with something not contractible. If you like spectra, you can say the like AGNs form a spectrum, and then loops infinity is like something that takes a spectrum and outputs a space. If you don't like this language, you should just view the thing on the right as like a single object, or a single space, but that it's not like, but there is no space AG infinity 2, and that you plug into this loops infinity functor. Maybe all I want to say.
Okay, thanks. Yeah, I was just gonna say that you gotta be careful with these definitions. To kind of repeating what Jeremy said, in a very, very watered down version, is we got an object loops infinity AG infinity. This makes sense just as a limit of the objects that we had, but you gotta be careful with the like each of them individually might or might not make sense. So loops infinity, yeah, like loops infinity, do not think of that as a functor.
In order to make them make sense, you need to leave the category of spaces. But if you don't want to leave the category of spaces, just think about them together.
Okay, so the scanning map, or what we call the scanning map, is this map above this one. I mean, I made it super ugly with so much commenting, but this map from configurations of S in R infinity into loops infinity AG. This is the scanning map. And a comment is that up to this point, we really haven't used that we're dealing with a surface. So we really haven't used that the dimension of S is 2. And really, up to this point, everything makes sense if we lose this this constraint, and we actually get interesting things. And for dimension of S equals 0, we also get something interesting that is very much related to what we did during the semester with Jeremy with configurations of points. Yeah, I don't know if I should say more about that, but yeah, just like I'm gonna leave it at that. Okay, so now it's time for a naive question. We have a map. We have a map here from configurations S into infinity to loops infinity AG. Is there any hope for this to be an equivalence in general? So I say this is a naive question because if we think of it for a bit, there is no hope for it to be an equivalence, because the left-hand side is something that depends on a choice of surface. And on the right-hand side, we have something very general. We have an affine Grassmannian. Well, okay, a construction on an affine Grassmannian. That really does not depend at all on S, on how we pick S. So yeah, this is not gonna spit out the result we want, that easy. So what do we do about that? Right? If there is no hope for this to be an equivalence, we could either just drop it or try to fix it. So how can one fix this issue? The left-hand side depends on choice of S, the right-hand side doesn't. So one idea to solve this is, all right, let's replace the left-hand side with something better, right? So the idea is replace S by an amalgam. I don't know if I'm pronouncing that right, but let's say amalgam over all choices of S, right? Since the problem is that the left-hand side depends on a choice of S, well, let's get rid of the choice. Let's choose everything, right? Let's replace S by all choices of S. Okay, so now we really do use that S as a surface, because S is a very nice surface at that. S is a close orientable surface. And we know that up to genus, for every genus, we have just one of those up to homeomorphism, right? So, so let's work with those, right? For every G, for every genus, let's choose one of them, and we're basically just like moving over all of the up to homeomorphism. We're moving along the surfaces that we're interested in. Okay, and how would we do that? Do this amalgam of this all choices of S. All right, so what we do is we pick a SG for every genus, and we pick it in a smart way such that we have we can form a limit of this sequence of choices, and we get this S infinity. By infinity means like the genus is infinity, right? And it kind of makes sense, right? If we choose S0 to be, this piece here, this cap that tops this off, and we choose S1 to be, everything up to this point, and then S2 to be everything up to that point, then we do see that we have natural mass between them, which are just inclusions, and we can take a limit, and the limit is going to give exactly this infinite genus surface. So a very natural construction. Okay, so S infinity is the union of an increasing sequence of compact surfaces SG1 of genus 1 and one boundary component. Right? So I forgot to say this. The one, we have a boundary component. Yeah. So the first one has this boundary component, and the second one has this boundary component, and so on, right? Right. Okay. And the space we care about, we really want to have this S infinity or this SG1s up to diffeomorphism. So we need to do something else here. So, right, so for each genus, so for each SG1, we fix a standard as G1, and we embed it in here. In R infinity cross this interval. And what's the point of this interval? The point is that the boundary component of this SG1 is going to lie, the boundary component is going to lie in this G cross R infinity. Right, so maybe going back to our picture here, and we choose this S01 and 11 and so on, like I said before, then along this axis, we have, from minus infinity, and then here we cut to 0. And we see that the model S0 that we picked, its boundary lives on 0 cross R infinity. And then the next model S1 that we have, S11, its boundary, well, if we cut here and we say that this is 1, well, it lies in 1 cross R infinity, and so on. So that's just describing this construction. Okay, and I told you that we wanted this up to diffeomorphism. So let CG be the space of surfaces of in here that are diffeomorphic to our choice, to our choice or standard choice SG1, whose boundaries coincide with the SG1, right? We want to glue them at the same boundary and consider that up to diffeomorphism. Okay. And all right, so I claimed that we wanted to replace this C as R infinity for something better, this amalgam of SG1s, of possible embeddings of S into R infinity. But the key thing that we needed for this C as R infinity is that it was an Adlenberg-MacLane space. That this is pretty much the only proof that I've that I have shown today is that this C as R infinity is an Adlenberg-MacLane space. Right? So in a similar way that we prove that, one shows that this construction CG is to an Adlenberg-MacLane space. Right? So it satisfies the same condition that we wanted for C as R infinity. Okay, so again, this is a claim that I am not proving, but okay. Yeah, I just want to give an idea of how this works. All right, so this CG is this Adlenberg-MacLane space, and we have inclusions of these S, this choice of S G's, and I already described above what the inclusion is like, and those inclusions are going to define inclusions on the level of the C's. And this is going to allow us to, so having these inclusions where we have like a directed system and we can take the direct limit. And taking the direct limit, we produce this C infinity. The C infinity is the object that we ultimately want. Okay. So far, are there any questions about this construction? Okay. So let me just I might be redundant here, but I'd rather be redundant than unclear. So what we had, so we produced a scanning map CSR infinity to loops infinity AG plus infinity 2. We produced that map. That map was no good. Not good enough. Right? So we replaced this guy by C infinity, where C infinity was a way of kind of eliminating the choice of S on the left-hand side. Right, and now we have the C infinity. And the ideal thing would be that now that we fixed this initial issue with this scanning map, then maybe this map is good enough. So one would hope that maybe this map is good enough and that we do get an equivalence there. Okay, and we get to the statement of the Madsen-Weiss theorem. So the Madsen-Weiss theorem says that there is an isomorphism of the homology of C infinity and loops infinity AG plus. Okay, so exactly what one would hope for after we kind of tweak the initial idea of the scanning map and resolve those issues. A comment here is that even more notation is appearing. We have a 0 down there, and what that stands for is a component. We choose a component. Right. So what that stands for is that the left-hand side is going to be path connected, and this loops is not. So we are just picking one path component of the right-hand side. That's okay. That's that notation, and that is the Madsen-Weiss theorem. So I guess that this slide is the objective of the session today, to get to this statement and to kind of understand that behind this isomorphism lies the idea of a scanning map, and that this idea of the scanning map is what produces this infinite loop space on the right-hand side. And okay, and I claim that this would allow us to compute the homology of mapping class groups. And apparently here on the theorem, we don't see the mapping class group of a surface. So we can take this statement of the theorem, and what we use is one uses the group completion theorem, which we have discussed in class, and harassability. Harassability, what allows us to do is to let's say replace this infinities by a range, and it tells us when this holds, like in which range this holds. So we know that it holds on the limit, but we would like to kind of ground that and take it back and have it. Okay. All right, and more precisely how we can actually use this to compute. So one uses this result to compute the homology of the mapping class group, precisely because of this homology of C infinity. It's just the limit over G of the homology of the CGs, but we didn't show. I claimed that CG is an Eilenberg-MacLane space. So this is the homology of the mapping class group of an SG, and if we start with an S in general, with all of its properties, its nice properties, a closed orientable surface. Then we have a homeomorphism to an SG. So really, if we want to find the homology of the mapping class group of the S, well, we can just do it on the SG, and that's exactly what this is allowing me to compute. Okay, so this is how we compute stuff with the Madsen Weiss theorem. Because another comment on this theorem is that just on looking at it, it seems like we have written the homology of something in the left that is something kind of geometric in nature, like it's a geometric construction, in terms of something in the right that seems to be something very complicated. It's this infinite loop space of this affine Grassmannian, and then we take this path component, right? It looks like something you don't want to compute, but it turns out that this theorem actually gives a tool for actual computations. And one such computation is Mumford's conjecture. So one of the things that it allows us to answer is Mumford's conjecture. Right? That was like that's a statement on cohomology. That was like the cohomology of a mapping class group of a surface is a polynomial algebra. And it gives the explicit polynomial algebra that you get. All right, so I think that this is it. So I'll stop here. And that's it. So I don't know if there are any questions.